Next in our series of lectures on remote sensing, we're going to start talking about various sensor options. So we're going to limit our discussion to passive optical sensors because that's what most people use. There are more sophisticated sensors out there, but they're really targeted toward much more narrowly defined applications. So after a general introduction to how satellites are designed and what kind of considerations go into that design, we'll talk about the most often used satellites, the multispectral moderate resolution sensors like Landsat and Sentinel-2. We'll talk about multispectral low resolution sensors, most commonly MODIS, and then we'll talk about the class of high spatial resolution sensors. So those are things like Iconos, QuickBird, and WorldView. And then we'll briefly talk about the constellation satellite approach that Planet Labs and similar organizations pursue. So we've talked about airborne sensors and their advantages. So they can be tailored to the needs of particular projects. You can send them out when and where you need them. There are a variety of sensors that can be flown in them that are available to collect data, and in general, a greater variety of sensor types because it takes a while for new sensor technologies to make the leap from airborne configuration to spaceborne configuration. You can adjust your spatial resolution just by modifying your flight altitude, whereas with a satellite you're locked in at whatever the satellite's altitude is. Flight altitude can also be used to circumvent weather issues, so you can fly below clouds if you need to. You can extend your mission operations until the observations you need are made. This is important in data collections of things like LiDAR, where you may not be able to collect all the data you need on the first day due to, for instance, cloudiness or rain. So you're able to some extent, to the extent that your wallet can handle it, fly multiple days and sit on the ground until you get the conditions you want. And the temporal resolution is flexible. That is, if you need data every day or every week or every month, you can get it, whereas with a satellite you are locked in to a certain temporal resolution based on the orbit. The advantages of satellite-borne sensors are an unrestricted ability to cover the Earth's surface. For instance, Brazil is very touchy about having people fly sensors over their country. And so the only way you can get that done is basically through intergovernmental negotiation or the private permitting process that they have, which is difficult to get through. Essentially, you have to hire a Brazilian organization to do the flying for you. Similarly, in China, I have done some LiDAR data collection over China, and they wouldn't let me have my data. They would let me have numeric summaries of small parts of my data, but they wouldn't let me have the rest of it, and I had to have a Chinese collaborator do the analysis on that data. The advantages of satellite-borne sensors: the collections are standard and multiple dates are easily compared. So they're always going to be at the same time of day. They're always going to be, within a reasonable margin at the same spot on the surface of the Earth. For most sensors, you're looking at the same sun illumination conditions every time. So that takes out a lot of the variability in analysis, and long-term archives are generally available. But it's at the cost of constrained flexibility. You might say, wow, there's a flood somewhere, and I'd really like to be able to pick that up with Landsat to help in first responders. Well, if it's going to be 16 days to get there, it's going to be 16 days. You're going to have to rely on something else. The nice thing about multispectral spaceborne sensors is the sensors are tuned for a wide range of problems. There are science teams, they have multiple interests represented on the science team, and each portion of the science team works out what their requirements are for their applications, and then the engineers are sent off to figure out how they can come up with a single sensor that's responsive to all of those applications. The problem is that it's unlikely that a perfect sensor or perfect sensor configuration is going to exist for an individual problem because we're trying to address multiple questions, and that always requires compromise. So while you could have one sensor that could provide high spatial resolution, spectral resolution, or temporal resolution, providing all of these in a single sensor would be prohibitively expensive. You can see pretty quickly that if you're collecting a large number of high resolution pixels with many bands and trying to do that, say every day, then you're going to run into limitations. Number one, on the hardware, because you're going to require a lot of pixels in your, for instance, your push broom sensor. But also, one of the main limitations for these missions is just the amount of data that one can download from one of these systems. There's simply no way to get certain amounts of data down, and you're competing actually with other missions because they all use an infrastructure that's responsible for collecting data from satellites and then moving it down to satellite dishes on Earth. So to some extent, you're constrained by the existing set of sensors that are out there. So sensors can be classified on the basis of trade-offs in their spectral, spatial, and temporal resolution that result from targeting particular sets of applications. But many of the most interesting uses of remote sensing come when instruments designed for one purpose were applied to another, or when multiple sensors are used to complement each other. So a specific example that I was involved in involved the Hyde Park fire, where we had Landsat images from just after the fire, which was a stroke of luck. But we also had higher resolution sensors that we could use in a photo interpretive capability. So we could actually go in there, figure out, lay out plots in a strandified random and clustered manner, photo interpret each one of those plots to say what percentage of the plot was burned, then use that data along with Landsat data to come up with a map of the percent burned for the entire Landsat image. So current capabilities of Earth observing satellites, these tend to fall out into discrete groups, again, because of what the kind of applications there are for them. High spatial resolution domain, these days it's about 0.3 meters to 4 meters. They keep pushing the technology for high spatial resolution sensors, and so that's gradually gone down from about a meter at the beginning of the high spatial resolution era to about, well, right now the highest spatial resolution sensor is about a quarter of a meter, but the Defense Department doesn't allow you to sell data with that high resolution. So I believe it's resampled to 0.3 meters. Doesn't seem like much of a difference, but apparently it's important to them. There's this sort of moderate spatial resolution of 10 to 30 meters, and that's going to be your Landsat and Sentinel class systems, which those are the ones we'll talk about the most. That tends to be a good scale for general land use mapping when you're looking at, say, a single date or a small number of dates. 100 to 500 meters, that's much more useful for systems that are going to map the Earth, once a day or even a few times a day, up to, once a week, for instance. And then finally, we have a coarse scale system that are between like 1 kilometer and 8 kilometer. And these are generally systems that are meant to collect data once a day to many times a day. So meteorological satellites, for instance, are generally around 8 kilometer spatial resolution, and they're collecting data every 15 minutes or an hour. Temporal resolution, you might have something like those meteorological satellites that are giving you images every 15 to 30 minutes. You might have something like the MODIS system that does daily data collections. You might have something like, we'll talk briefly about the now defunct Rapid Eye system that gave you 5-day temporal resolution. And then bi-monthly, twice a month, things like Landsat generally cover the Earth, every 16 days. Finally, we have 3 spectral domains. One of them is panchromatic. Well, that's just one band. The other is, or another, is multispectral, so say 2 to 6 or maybe 2 to 8 bands now. And finally, you have hyperspectral domains, so that's between 10 and 100 bands. So that's the general introduction to what kind of sensors are out there. We're now going to start talking about the multispectral moderate resolution sensors. So Landsat is the sensor that immediately comes to mind when you're talking about this kind of sensor. So it's the longest, it's the most comprehensive record of the Earth condition ever assembled in the Eros Landsat archive, which includes almost all of the images that have been collected with Landsat. There are more than 6 million images, which is 171 billion square kilometers, that were collected from 1972 to the present, and they span the globe. Now, they don't very often do water collections, and they don't very often do Antarctic and Arctic collections, because once you get up to the poles, the lighting conditions become poor. There has been an attempt to do an Antarctic mosaic that was done with Landsat. All Landsat images are available to anyone at 0 cost. It used to be that you had to pay for these things and then sign a pledge that said you wouldn't share them with anyone else. And that worked out really well. People definitely always adhere to the not sharing pledge. So each year, 5 million images are distributed to users in over 180 nations and territories. And it basically all starts with Landsat. Early land viewing satellites were designed for broad-scale meteorological observation, so basically looking at clouds and cloud distribution patterns. Landsat, which stands for Land Satellite, was the first one tailored specifically for systematic observations of the Earth's surface. It was designed in the late 60s, launched in 1972 with broad scientific support. It was just a big U.S. investment. There were no guarantees that the program would succeed, and In fact, it wasn't thought that this was going to be what wound up being so far almost 50-year program. Um, and the experience provided the operational knowledge and the knowledge of feasibility that then spurred worldwide development of similar remote sensing systems. Um, so the Landsat system consists of spaceborne sensors that observe the Earth and then transmit information to ground stations that receive and process data for dissemination to users. There have been 8 Landsat satellites. There's a 9th one that's supposed to be flown in December of this year. And these were really, there were sort of 2 sources of motivation. One was the views that were gotten from meteorological scientists, which started making it very clear that the Earth didn't look like the way that they had thought about it. And the other would be the Apollo mission photographs, which were, it's hard to imagine now, but were really stunning, had a real effect on public knowledge. This was about the time that the environmental movement was getting going, and the notion that the Earth was one big system is one that was readily captured in those few images, those few color images that came from the Apollo missions. So Landsat 1 was originally referred to ERTS-1, the Earth Resources Technology Satellite, but apparently someone in public relations said, listen, let's call it something a little catchier, so it became Landsat. And it really was an experiment to test the feasibility of collecting multispectral Earth observation data from just an unmanned satellite platform. So again, they had no idea what this was going to become. There have been a number of sensors that have been on the Landsat series of satellites. Until Landsat 8, those were the return beam Vidicon, which was basically a TV camera pointed at the Earth. That's the sensor that they thought was going to be the main sensor. So this would be on like Landsat 1. But it turned out that the multispectral scanner, which is much more like a system that we would think of in terms of a scanning remote sensing system, was the one that people found very popular. And then later on Landsat 4, the thematic mapper, which is sort of an improved version of the multispectral scanner, was launched. So the most popular instrument in the early days was the multispectral scanner. Later you had the thematic mapper. Each of these sensors collated data over a swath width of about 185 kilometers, with a full scene being defined as 185 kilometers by 185 kilometers. Note that these are cross-track scanning systems, so there really is no scene height. The scene, there's a swath width that's a real value because it's determined by the mechanics, but you can cut off a Landsat scene anywhere you want. But it just so happens that people like square grids, and so the full scene is defined as 185 by 185 kilometers. The current system now on Landsat 8 and to be launched on Landsat 9 is the operational land imager, which is an improved version of the thematic mapper. It adds a few bands, and it is a push broom system. If you recall, we talked about the problems that Landsat 7 had with a scanning system, and so it was decided that for Landsat 8 and going forward, you would have push broom systems that wouldn't be reliant upon on that extra mechanical devices that you need for an across-track scanner. All Landsat satellites, we've talked about this, they're placed in a near-polar sun-synchronous orbits. The first 3 satellites were at altitudes around 900 kilometers, and therefore they have revisit periods of 18 days, while the latter satellites all are about 700 kilometers and have revisit periods of 6 days. And all the Landsat satellites have equator crossing times in the morning so that you can have optimal illumination conditions. That difference between 18 days and 16 days results in a different number of paths. So the paths are the north-south distribution of the satellite images. The rows are, the paths are the east-west distribution of sensors. So there's a path that crosses at, say, 0 degrees west, and then another path that crosses at whatever that would be, 15 degrees west, then another at 30 degrees west. There are also rows, and those follow latitudes. So again, coarsely, they're, one at the equator, one 185 kilometers above the equator, etc., etc. So paths are the columns, rows are the rows. The important thing to know is that subsequent rows, so as you're going north-south, are sampled continuously. It's a scanner success there. It's not frame capture. And then adjacent paths are sampled 1 day later. So that means that you have continuous weather conditions north-south. So if you've got, if you're socked in by clouds at one particular path row combination, you're probably going to be socked in by clouds at the next further south path row combination. However, the next adjacent path is sampled 1 day later. And so by then, weather conditions may have changed. So it just makes it very different when you're doing mosaicing, whether you're working north-south or east-west. To give you an idea of the kinds of bands that are in each one of these sensors, MSS has 5 bands. The bands are labeled 4, 5, 6, 7, 8. And the reason they're labeled that way is that the reverse beam Vidicon is given the numbers 1, 2, and 3. It's just a legacy issue. It kind of represents a strange way of thinking about the whole problem, but a lot of these things you just have to shrug your shoulders and say, well, they were the first ones to do it, so they're allowed to screw up some. So we've got a green band, a red band, a near-infrared band, a second near-infrared band, and then a thermal band. The optical reflective bands are about 79 by 79 meters. So that's for bands 4 to 7. And the thermal band is 240 by 240 meters. And again, that's just because of sensor technology. There's less energy at that portion of the spectrum, so you need larger pixels to collect it. It's only 6-bit values, so you can only represent values of 0 to 63 or 64 levels of grayscale, which is a real problem when working with this data when you want to do things like forest classification, because you know that a lot of other things are as dark as forests, and it would be a real help to have those extra 2 bits that you get in Landsat 7. The MSS flew on 5 Landsats, so it flew on the 18-day Landsat 1, 2, and 3 sensor satellites, and then on two 16-day Landsats 4 and 5. Again, altitude about 919 kilometers and a swath width of about 185 kilometers. That 18 to 16 day coverage or temporal resolution is important because if you think about it, if you've got an 8-day temporal resolution, it means that you have more paths than you do with a 16-day. And so as a consequence, the first Landsat's paths don't line up precisely with the second set of Landsat paths, the one we used from Landsat 4 through today. So as a consequence, you get the problem of having to mosaic early MSS data together in order to have a tile that includes both the Landsat, say a Landsat 4 TM image and a Landsat, 3 MSS image, and it becomes a tremendous pain in the neck. Fortunately, if you're interested in that kind of work, there was a group that sat down and actually worked out nice mosaics that are all targeted to the year, like, I want to say it's like 75, 80, 85, 90 maybe, and came up for the United States and Mexico with stacks of images where they found the best possible images to overlap with the second set of 16-day repeat paths. When we go to Landsat 4 and 5, the thematic mappers on these systems. So what changes have we made here? Well, we've added in blue as band 1, and we've taken out that second near infrared, and we've put in 2 shortwave infrared bands that are labeled, strangely, 5 and 7. I don't know if I've gone over this, but I find it a funny story, so you're going to hear it again. Which is, originally they thought that they could put 6 bands on Landsat 4 on the thematic mapper. And so they developed all of their documentation with 6 bands in mind. And then someone realized, oh wait, we could squeeze a 7th band in here. It would be another mid-infrared band. And so they were left with a choice, one of which was to rewrite all of the manuals to make the new mid-infrared band, band 6, and move the existing band 6, which was thermal infrared, to band 7. And that way, there'd be all the spectral values would be in order. But this is, back in the type of typewriters. So nobody wanted to have to go back and do all that editing and make sure that they got every single example. And so what they decided to do was just to make the second mid-infrared band, band 7. And so then they could just type it at the bottom of tables and not have to worry about reformatting the original documentation, which I find to be a clever solution. It's probably the one I would have voted for. Thematic mapper has a dramatic increase in spatial resolution, or a dramatic improvement in spatial resolution. So there are 30 by 30 meter bands for bands 1 to 5 and 7. So visible, near, and mid-infrared, and then 120 by 120 meters for band 6, the thermal band. These are 8-bit values, so that's an incredible improvement. All of the thematic mapper data was collected with on 6-day orbits. Landsat 7 was very much like, Landsat 6 was very much like Landsat 5 in terms of having a thematic mapper. It was called the enhanced thematic mapper, which meant, I think, that it had just that it had better spatial resolution. The reason I don't know the answer to that question is that Landsat 6 immediately took a dive in the ocean and was never operational. So on Landsat 7, it's called the Enhanced Thematic Mapper Plus is the sensor on it. And the reason it has like two, it has both enhanced and plus, is because you have this missing Landsat 6. Landsat 7 adds an 8th band. That's a 15 by 15 meter panchromatic band, and that is used to help increase the spatial resolution that you can achieve with the other bands. And we'll talk about that when we talk about pan sharpening with high spatial resolution data. The spatial resolution on the thermal band is 60 by 60 meters. So that's the other big difference. And of course, Landsat 7 had the problem with the scan line corrector, so it only operated for 4 years before it seized up and stopped giving the high quality data. Fortunately, it's really hard to figure out how long satellites are going to last. So Landsat 5, all of these systems are, they're constructed with a budget assumption that they're going to last for 5 years. Landsat 5 lasted for 20 years, and you never can tell. You get a random cosmic ray, and all of a sudden your system is faulty on day 1, or you luck out and suddenly you get 20 years on your satellite. You can't really tell. So this is a comparison of the operational land imager that is on Landsat 8 and the TIRS, which is the thermal infrared sensor on Landsat 8, with the earlier, this is Landsat 7 data. So if you look, first of all, they reorganized the order of the bands, so that's nice. So if you look, the first band now is a coastal aerosol band, so that helps you in your coastal zone observations. It's going to have way more Rayleigh scattering, but it's going to help you correct for the Rayleigh scattering in the blue band. Blue band's the same, green band's the same, red band's the same. Near infrared is the same. SWIR 1 and SWIR 2 are the same, only now they're in the correct order. They're band 6 and 7. Band 8 is the panchromatic band, which in Landsat 7 included both the green, red, and near infrared portions of the spectrum. Now it only includes the green and red portions of the spectrum. Band 9 is a cirrus band. It's kind of sitting out there all alone, and its job is to detect high altitude cirrus clouds that might otherwise contaminate the spectral signatures that you would get from the other bands. Band 10 and band 11 are two thermal bands, each one at 100 meters, and each one having more or less adjacent portions of the spectrum. The reason why you have two is that you can do comparisons that allow you to correct for emissivity. They're called split window approaches to thermal data processing. And so having those two bands makes the thermal bands more useful than just having one. So the advantage of Landsat data, we have this synoptic view, which just means that it covers a nice chunk of the Earth at once. You know, that happens to be convenient. If you're dealing with, Colorado, then you're talking about maybe 40 images to cover the whole thing. That's not too bad, to be able to do that at a 30-meter spatial resolution. Obviously, it's got a digital format, so you can do quantitative processing and analysis. It kind of has the right spectral information content, particularly with the thematic mapper going forward. No one's really come up with another band that, gosh, you'd really like to have. The only thing that was added was that cirrus band for atmospheric correction, and that is an advantage. But no one said, oh, we really ought to be hitting this other part of the shortwave infrared. It's got a 16-day repeat cycle. When we get Landsat 9 up, we should have 8-day repeat cycles. And that's something that people have thought about for a long time, particularly for agricultural monitoring. It's relatively low cost. Both the sensor itself does not cost that much money, and doesn't cost anything now to download the data. It's a consistent scale and format, so dealing with one image is very much like dealing with any other image. It's applicable to multiple data problems, I'd say. That is, it's good for soil mapping, it's good for agricultural production mapping, it's good for forest age mapping. There's a heck of a lot that you can get done with one Landsat scene. And you do get nearly complete coverage of the Earth's surface, although there's no ocean coverage. I think at one time there was an attempt to get ocean coverage. There is coastal coverage, but I think that the actual deep ocean has maybe once been surveyed. The limitation is small scale of the data, that is coarse pixels. Cloud cover is a problem, but it's always going to be a problem with an optical sensor. And that 16-day cycle really is inadequate for many things. Like I was saying, we're looking forward to getting an 8-day cycle with Landsat 9. And just a little historical callback here. In '91, when I started my career, Landsat 5 seeds cost $4,500 per scene and could not be shared. And that was a lot of money. That's a lot of money now, but it was probably more like $10,000 in today's dollars in 1991. But as of 2011, all data is now archived and are free, as are things like MODIS. Okay, so now we're looking at ESA, the European Space Agency, and they have had a system or a suite of systems named the Sentinel systems. Sentinel-1 was SAR, Sentinel-3 is low resolution optical imaging and ocean altimetry. Sentinel-4 and 5 are atmospheric monitoring. And then Sentinel-2 was high resolution. I wouldn't call it high resolution, it's moderate resolution optical imaging. So there are two Sentinel-2s operating in a twin configuration. There are 13 bands in the visible, near infrared, and shortwave infrared. But not all of those bands are collected at all resolutions. There's 10-meter data, 20-meter data, and 60-meter data. It's a sun synchronous orbit at about 790 kilometers. So it's doing 14 plus 0.3 revolutions per day with the local time of crossing the equator at about 10:30. And the swath width is 290 kilometers, so a bit bigger than Landsat. It's systematic. It's all land and coastal services between -56 and +84 degrees latitude. It revisits every 5 days at the equator when you consider having 2 satellites, okay? And that's, you know, every 5 days you should get 100% coverage of the area it covers, unless you consider clouds, in which case it's going to be a longer revisit period. It can do lateral pointing, so you can shift the satellite off nadir in order to pick up areas adjacent to the current path. And so any point on Earth can be observed within 1 or 2 days, provided it's not cloudy. These are push broom sensors, and the lifetime is supposed to be 7¼ years, extendable to 12 years, but again, it's very, very difficult to know how long a system is going to last in space. So this gives you an idea of what bands and how they're distributed among the wavelengths and spatial resolution. At 60 meters, we have bands that are probably mostly going to be used for atmospheric correction. So we've got a blue band and near infrared band and a shortwave infrared band. At 20 meters, we have a series of bands there that are kind of red edge between red and near infrared band, and then 2 shortwave infrared bands. And then finally, at 10 meters, we have sort of a blue-green band, a green band, a red band, and a near-infrared band. And it's nice, they give you these nice diagrams where they've calculated out the revisit time over various parts of the Earth, and some are with 2 satellites. So considering cloud cover, so if you've got 2 satellites, then you know it's between 0 and 5 days. They're mostly going to be close to 5 days there for visit times. And then as you go further north, you get longer and longer periods between good observations. You know, you might get, geez, in the England, you might be 85 days between a good coverage. And that is only a 15% cloud cover that they're determining as a, you know, as a cloud-free day. So put that in your tea and drink it. Okay, so now we'll move on to MODIS. So there are 2 satellite platforms that carry MODIS. One is called Terra, and one is called Aqua. They actually had a competition to come up with those 2 names. Each of them has a number of sensors on them. They both have MODIS. Terra has Aster, which is a high spectral resolution thermal sensor, Miser, which is a multi-angle sensor, and then Ceres and Moppet, which are both atmospheric sensors. So MODIS is carried on the Terra platform, which was launched in December 1999. It's then also carried on Aqua, which was launched in 2002 and has a similar suite of sensors. So you get 2 images, almost 2 images per day for the Earth surface. So in Terra, you get a morning overpass. Aqua, you get an afternoon overpass. And so MODIS provides continuous global coverage every 1 or 2 days, mostly 2 days with the Aqua coverage, and collects data from 36 bands. As with Sentinel-2, those bands are not all at the same resolution though. There are two bands, bands 1 and 2, that have a resolution of 250 meters. 5 bands, bands 3 to 7, have a resolution of 500 meters, and the remaining bands have a resolution of 1,000 meters, or 1 kilometer. And then the swath width for MODIS is 2,330 kilometers. So in order to get that fast revisit, you need to have a very wide swath. Give you a sense of what those bands are. Those first two high resolution bands at 250 meters, they are red and near infrared. So those are primarily used for vegetation, and then cloud boundaries and aerosol boundaries. The next 7 bands are used for, the next 5 bands are used for land properties. So that's when you're going to have blue, red, you're going to have near infrared, and then 2 mid infrareds. Those essentially are going to allow you in those first 7 bands to match thematic mapper bands. The next set of bands are associated with ocean characteristics. And so you can see there are a number of blue bands there. 405 to 420 nanometers, 438 to 448 nanometers, 483 to 493. These are narrow bands that are used specifically for picking up things like phytoplankton density and biogeochemistry that's going on in near shore waters. The rest of the bands are all atmospheric, and so I don't have a background with them, but it's things like, you can see, water vapor, surface and cloud temperatures are also done at 1 kilometer. Atmospheric temperature, looking for the presence of cirrus clouds and water vapor in the atmospheric column. A couple of a band in there for cloud properties, a band in there to detect ozone, more temperature bands, and then cloud top altitude, which, as you can see, is also done with thermal bands. Now, the interesting thing about MODIS is it was part of a EOS, or the EOS initiative, which was Earth Observing Science. And so the push then was to take remote sensing out of the hands of just remote sensing scientists and move it into a place where people from a variety of backgrounds were able to work with it. So as a consequence, the solution that the science team came up with was to have multiple products. Landsat, traditionally, you would get back a radiance value, so just an overall brightness. It would come as a digital number that you would then convert to radiance, and then you'd have to go through a separate set of analyses to get at a surface reflectance. With MODIS, you're provided with a surface reflectance as a data product. You're provided with land surface temperature, an estimate of emissivity, a land cover type, a series of vegetation indices, so you don't have to calculate them yourselves, thermal anomalies and fire. That's like a quick alarm product that tells you whether something has suddenly become hot. Leaf area index and fraction of photosynthetically active radiation, that's FPAR. There are then model-based products like net photosynthesis, which again we'll talk about, net primary productivity, the evapotranspiration from the surface, the resistance to evapotranspiration, BRDF, bireflectance distance function, bireflectance distribution function, which kind of tries to correct for the different angles at which you're observing the surface of the Earth. a product that looks into just giving you whether or not there's been a vegetation conversion from one type to another, and then a vegetation continuous fields that we'll discuss. If you look on this table, they're all produced at various spatial resolutions and temporal resolutions. So for instance, land surface temperature is produced daily at a 5 kilometer spatial resolution. And net primary productivity is produced yearly at a 1 kilometer spatial resolution. That green box there shouldn't be there. There is not a yearly net primary productivity produced daily, because that makes no sense. But then, like, surface reflectance is produced at an 8-day 500 meter spatial resolution, a daily 500 meter spatial resolution, an 8-day 250 meter resolution, and a daily 250 meter spatial resolution. Break up the various different land products from MODIS into 3 categories. One of them is the energy balance product suite. The second is the vegetation parameter suite. And the third is the land cover land use suite. So here we have an example for Southern Africa, where on the left we're looking at a surface reflectance that has not been corrected for aerosols. So you can think about this as a top of atmosphere reflectance. That is everything the sensor is seeing from the lens itself down to the land surface. And on the right, you've had aerosols corrected. And you can see it's a much clearer image. There's much better contrast. You're going to have a much better time trying to do, say, land surface classification on an image like this than you would if you had just used the image on the left, which is sort of a top of atmosphere correction. Now, I've talked about the fact that MODIS images come in various day lengths. That is, there's an 8-day product, there's a 32-day product, 16-day product. And in order to get those products, you're taking multiple images of the same area and stacking them up and asking what the best pixel, what's the clearest pixel that you can find from that stack of pixels. Okay, so you're saying over, say, 8 days, what's the best pixel that I got for a particular area? And the rule that's generally used is to find the pixel that has the maximum NDVI. And the reason is that the more aerosol and other scattering effects are involved in a particular pixel, the bigger the red reflectance is going to be. All right, so you think about Rayleigh scattering, it's going to affect the red reflectance much more than it's going to affect the near infrared reflectance. And therefore, because that red reflectance is going to go up, the difference between the red reflectance and near infrared reflectance is going to go down. And so as a consequence, the NDVI that you get for that pixel will be lower. So you can use this maximum NDVI approach to take any number of daily images, or it could be, bi-monthly images, could be Landsat data, and get the best pixel for a time period. And that's tremendously useful because when you're looking over large areas, the chance that you're going to get good quality pixels in a single image is low. And so this is one way to get around that. And that's what it means when we talk about these these 8-day composites. In addition to doing compositing, this image, for instance, is a 16-day composite. There's also the BRDF adjusted reflectance, so bireflectance distribution function. And when you've got a swath that's 2,300 kilometers or so, the sun angles at nadir are going to be very different than the sun angles that you're going to be seeing at the edges of the swath. That is, the illumination geometry of the sun to the surface up to the sensor is just going to be very different at the edges of the swath. And so one of the other things that the MODIS system does is it creates a BRDF adjusted reflectance. So it adjusts for those angular effects. And the nice thing about EOS is that, or MODIS, because it's part of the EOS system, is that that BRDF adjusted reflectance is then used in subsequent calculations. So in some sense, all the products depend on the other products that are sort of more basic in the processing stream. Another automatic product is the image and snow map. We know that clouds and snow have very different spectral characteristics in the mid-infrared, and this product just takes advantage of that difference to classify out cloud and keep remaining the snow areas. And so here we have snow, we have land, and we have cloud. And then you can look at the change in the snow extent between various composite periods. Here between November 1st and 7th of the year 2000 and November 8th and 15th in 2000. And you can see that there's greater snowfall that's occurred between the 8th and the 15th than there was between November 1 and 7. Now, the depth of the snow is not something you know, but this does give you an idea in coverage, and Stephanie Camp of the ESS department has worked on just using this information about snow cover to actually generate estimates of runoff in streams. Land surface temperature product. So this is a daytime 1 kilometer land surface temperature. It's being shown at a 5 kilometer browse resolution, but so there's both the 8th day and a daily land surface temperature that's taken, and you can see it's pretty much hot where you'd expect it to be and cold where you'd expect it to be for this time of year. And of course, the empty areas are all cloudy areas. So those are your energy balance product suite parameters. Now about vegetation parameters. We know that either a simple ratio of NIR to red provides valuable vegetation index information, and the NDVI provides a level of improvement above that. On the image there to right, there's also displays then EVI, an enhanced vegetation index, that tries to bring in blue in order to correct for the amount of soil cover, particularly for dryland areas. And there's been some evidence that it works, but in fact, I think most people, for most purposes, continue to use NDVI because it's simpler. So here we have, hopefully, in your presentation, information about greenness over the course of time. okay, with NDVI and EVI, and just showing you the greening up and browning down, particularly in the northern hemisphere, of vegetation as a function of time. And it turns out that this information is tremendously useful. There are the obvious things like looking at vegetation health and looking at crop productivity, but also individual vegetation types have individual or unique signatures. So for instance, if you're looking at evergreen forest versus deciduous forest, you can tell, just simple logic, that the evergreen forest is going to remain much more consistent than the deciduous forest. Mixed forest is going to act somewhat in between the two types. So that gives you an immediate idea of what kind of forest you might be looking at. Does it have high LAI, or high NDVI? Yes. Okay. Is it highly variable or isn't it? If it is highly variable, then it's probably deciduous. If it's not, then it's probably evergreen. The one caveat to that is that, in fact, conifer forests or evergreen forests, particularly in areas like Colorado where they don't have full cover, do show seasonal variability in greenness. And the reason is that you see the green background vegetation, the ground vegetation, greening up in the spring. And so there's some added greenness that these evergreen forests, whose canopies don't change very much in greenness, the canopy as a whole, when you include the ground surface, does in fact get greener and less green over time. And here's just another example of this, of greenness through the months of 2005, and showing in particular how the very dry areas of the Midwest and the north central states become green over the summer months and then back down to brown. Another data product that's generated is ice extent and temperature. So those studying the polar ice can get estimates of that without additional processing. Sea surface temperature, which is tremendously important, number one, for fisheries. I think we've talked about this, looking for the signature of upwelling ocean waters that provide nutrients that support the food chain in places like off the coast of Peru. Also useful for weather forecasting. So the signature of an El Nino versus an El Nina year is the temperature of the water at the surface of the ocean in the equatorial region of the Pacific. Leaf area index and FPAR, which is the fractional photosynthetically active radiation absorbed. So leaf area index is basically the number of layers of leaves above a point on the earth. So if you think about just sort of driving a spike through, from the top of some kind of vegetation down to the ground, it's how many times that spike is going to touch or intercept a leaf. So, low leaf area index biomes include things like, grasslands and scrub areas. High leaf area index areas include things like tropical forests, where you might get 12 layers of leaves above the ground surface at any one point. A similar product is FPAR. So PAR is photosynthetically active radiation. It's basically the blue and the red portion of the visible, and FPAR is the fraction that's being absorbed. So if you can see, a high level of FPAR is being absorbed. A high level of PAR is absorbed in forests globally, and in deserts, not so much. More complicated products that are created from MODIS. This is a global photosynthetic um, productivity map created by the University of Montana. And basically what it's saying is how many grams of carbon are being created within the leaves of plants per meter squared per day. Now that's not the total carbon dioxide uptake because it's the gross primary productivity. Net primary productivity, in order to calculate that, you need to know how much is being respired or either by the photosynthetic process itself or in the evening when metabolic processes are going on. This is not, this is a much more complex product. It's based on net primary productivity, and specifically it's based on the models of net primary productivity. But I love the image, so I always show it. What you're seeing is a sensitivity analysis. So for any given point on the Earth, you can look at the model results for net primary productivity and say, what's the limiting factor? If areas in red, the limiting factor is water. So there's simply not enough water there to have high productivity. Areas that are blue, there's a temperature limitation. And so you see in the northern latitudes a lot of areas that are blue or cyan because those are areas where you're not getting high enough temperatures in order to create more primary productivity. And then finally, areas that are green are radiation limited. That is, there's enough water and it's high enough temperature that you can create even more vegetation if you had more light. And that's what I find interesting is that even in some of the temperate forests, but a lot of the tropical forests, they're light limited. That is, their photosynthetic mechanism is well structured enough that they could use even more light. And so cloudiness is the big limitation there. If there were fewer clouds, of course, if there were fewer clouds, you'd have greater productivity. If you had fewer clouds, you'd have less water. So then you'd have other limits to your productivity. But I've just always found that fascinating. So you've got the blue, teal areas or cyan areas that have high radiation limitations, like at the high latitudes, and temperature limitations at that same area. You have the red areas where you have water limitations, so the desert areas. It also shows just how dry it is where we are, kind of puts us into context that we're among the driest places on Earth. And then those green areas that are primarily radiation limited, and that's due to cloudiness. Finally, the land cover and land use suite of MODIS products. There is a 1 kilometer land cover product that's created every 90 days. So it uses that the view angle corrected, the BRDF corrected surface reflectance, and for all of the 7 land bands, that is the 250s and then 500 meters. It uses spatial texture from 250 meters. It used the vegetation index, snow cover, land surface temperature, and estimates of the bidirectional distribution function information itself. in order to create a 17 class land classification. And then there are test sites for training all over the world. It's a very sophisticated algorithm. It uses multiple approaches to get at this final answer. So this is from two 16-day periods, just comparing MODIS, the more advanced, more recent sensor, with AVHRR land cover. And you can see quite a difference in being able to bring out a wider range of distinctions in, say, forest cover than you were able to with the earlier sensor. There's a change detection product, okay? So this is a change vector approach where you can immediately pick up whether or not an area has, for instance, as in this case, flooded during a time period just by knowing what changes in reflectance have occurred. It's another product, a tree cover map. There's a series of bands. You'll see bands or layers that are created that are the vegetation, continuous vegetation cover product, which gives you the percent tree cover, the percent soil, and percent herbaceous cover. So this is the percent tree cover map for the United States, and it's separating out the two kinds of green cover, woody and not woody. Then this is the continuous field product shown as RGB, where red is woody vegetation, green is herbaceous vegetation, and bare ground is blue. So you can see deserts and Greenland are blue, areas with high woody vegetation, forests are red, and then areas that are dominated by grasslands are green. The nice thing about this product is that, particularly for places like Africa, it shows where there's a mix of herbaceous and woody vegetation. And of course, that's very important because those semi-arid areas support a big fraction of the Earth's population, and the shifting of woody to grassland vegetation is important there. There are then the MODIS fire products, and there are 3 fire products. There's a 8-day composite fire product. There's a summary fire data product that tells you about, the composite is going to tell you if there was a fire there at any point. The summary is going to tell you something about how much fire there might have been during that time. And then finally, there's a daily fire product that's done at coarse resolution, 5 kilometers. This is a very important data product because the U.S. Forest Service uses this. Since it's MODIS, you can get a twice-day estimate of where there's fire. So you can get early detection, and you can get extent of fire that you can use, and they do use in their daily fire planning. Okay, now we're going to talk about high spatial resolution sensors. So these are kind of I think of it as a relatively recent development. The Land Remote Sensing Policy Act of '92 allowed the licensing of these satellites. Before that, it was considered national security risk to have people looking at things at too high a spatial resolution. ICONOS was the first U.S. commercial satellite. ICONOS 1 was launched in April 1999. That was lost in space. ICONOS 2 was launched in September 1999, and that's the first we have data from. These sensors in general follow the same pattern, which is they have a panchromatic band and and then a multispectral suite of bands. The multispectral suite of bands has a spatial resolution that's 4 times, well, the spectral resolution is 4 times that of the panchromatic band. So if the panchromatic band is 1, then the multispectral band is 4. These are all in sun synchronous orbits, about 10:30 a.m. overpass locally, and they have a repeat coverage of about once every 3 days. In general, the entire satellite can be turned so that you can do off-nadir pointing, either for collection of stereo coverage or for fast collection of a scene in an area that there's some kind of time-sensitive need to pick up an image. And these systems do not, as a rule, collect data everywhere all the time, like something like Landsat. They collect data basically where they're paid to collect data. You send them an area of interest, and they send you a quote, and if you accept the quote, then they're going to look at that area the next time that the satellite comes around. So here's a variety of different sensors that fall into this characteristic of very high spatial resolution sensors. The spectral resolution, again, it follows, one of 2 patterns, a panchromatic band and then a blue, green, red, and near infrared band. The panchromatic band, second column, will generally have 1/4 the pixel size of the multispectral band. And that's because if you're looking at the whole suite of the panchromatic, which can either be all the visible or all the visible and the infrared, you're just observing more energy than you would be if you were looking multispectrally. And so because you have more energy, you can have smaller pixel sizes in the detectors that actually record the image. And so that's why you get this 1 meter, 4 meter, or 0.6 meter, 2.4 meter. One of the lower resolution systems in here is Rapid Eye. Rapid Eye was full coverage. It no longer runs, but it was full coverage at 5 meter spatial resolution, and I personally miss it because I thought it was a good. It added flexibility that you wouldn't otherwise had from the other suite of systems. And they create beautiful images, right? So like here's the Eiffel Tower, here's the Millennial Ferris wheel. I forget what they call it. It's in London. And this gives you an idea on the left of the highest spatial resolution systems from aerial photography, and then sort of a 1 meter spatial resolution fused panchromatic multispectral image, and then Landsat on the right. And you can see your satellite data product there looks a heck of a lot like your aerial photography product. And so that's one of their real strengths, is you can use them in a photo interpreted context. Digital Globe has the most of these satellites. So their satellites come under the word QuickBird, WorldView 1, WorldView 2, and they also do aerial data collection. And Digital Globe is actually right down in Longmont. So they actually hire a great number of remote sensing scientists. WorldView 2 is an exception to the rule here. And this is a Digital Globe product. QuickBird follows the general rule, which is it's got a panchromatic band from 450 to 900 nanometers, It's got blue, it's got green, it's got red, and it's got near infrared. Worldview 2, on the other hand, puts in a lot of interesting things. It puts in a coastal blue channel that allows you to do better atmospheric correction for the blue band, but also penetration into water that's better than in the blue, and adds a near infrared 1 and near infrared 2, as well as a red edge band. So that red edge band gives you information about how fast the low reflectance in red increases into the near infrared for vegetation. And so that's a vegetation health indicator. And it's got a revisit frequency of every 2 to 3 days, and can off nadir point plus or minus 30 degrees nadir. So this is a very sophisticated system. Worldview 3 is even more interesting because it adds in 8 shortwave infrared bands. So it's got a panchromatic nadir band at 31 centimeters, a multispectral at 4 times that, or 1.24, and then it's got a shortwave infrared nadir at 3.7 meters. So I guess that's what, yeah, about 3 times the multispectral pixel size. That is a very forward-thinking design, because most systems that do away with the shortwave, and this allows you to have more information about the things we've talked about, soil moisture, and it also allows you to match up better with Landsat. So all in all, a very sophisticated design. Rapid Eye, these were 5 sun-synchronous Earth observation satellites, so large area, multispectral images, frequent revisits with high spatial resolution, 5 meters, which we found was adequate for photo interpreting fire damage at the Hyde Park fire. There's a beautiful image from Rapid Eye. And another is an agricultural landscape. So the advantages of high spatial resolution, or some people would say hyperspatial data, well, it's high spatial resolution, and it comes with multispectral imagery as well, and it's the highest resolution data ever available to the civilian mapping community. It has high radiometric resolution, so that allows you to get at differences in things like forests where they're going to be dark, and so you can really use that extra radiometric resolution. It has high location accuracy, and you can buy orthorectified images from the various providers, so it's ready for input into GIS. It's familiar, it can be interpreted like aerial photography, although it also, for the most part, can be interpreted using conventional digital imagery techniques. You can get timely imagery, that is, you don't have to wait 16 days to get an image. You can, if you can pay for it, you can get an image generally in 1 or 2 days, particularly if you're not very specific about what sensor you need the data from. Something will be passing over. And as we'll talk about, Planet Labs as a solution that's distinct from this one that can get you images the same day if you need them. Repeatable acquisition, so it's possible to get images that are taken from the same time of day, from the same place. Rapid delivery, that's one of the things they make as part of their promise to you. It has an extremely long focal length, so you can capture some terrain relief information. And some of the sensors have 4 nadir and aft looking linear CCD arrays, so push broom arrays. so that you can get in-track stereo strips. So you get one looking forward, one looking aft, and all of them have pointing capabilities. So you can generate, again, either cross-track, so from one track or path to the next, or a long track. You can either be pointing forward and then rotate the satellite so it's pointing back at the same area, and then get a stereo image that you can generate from that. Limitations, I mean, the spatial resolution is lower than aerial photography. Scheduling acquisitions at desired times is sometimes more difficult than anticipated. The U.S. military is the biggest funder of these, of data collection from these satellites, and if you have an acquisition that conflicts with theirs, then you don't get your image. They're small images, as we'll see, maybe 10 by 10 or 20 by 20 kilometers. The view angle may vary from image to image. So if they're doing something off nadir and they're coming around and still rolling to get back to the normal nadir image, you might be able to pick up a different view angle than you would otherwise. Classification can be difficult because, rather than with something like Landsat looking at sort of an average forest condition, you're actually looking at pixels of shadow, pixels of shaded foliage, pictures of bright foliage, pictures of rock, pictures of all sorts of different things. And in a standard classification, each one of those is going to come out as a class. So it does make that more difficult. And finally, cost. I mean, it's a lot of money, it's thousands of dollars, and their criteria for a successful image is 20% cloud cover or less. So you may collect an image over an area, your particular area of interest might be covered with clouds, and they'll say, hey, it's less than 20% clouds, and so you need to pay for it, which doesn't do you very much good. And so this gives you an idea of the coverage, what a single Landsat scene looks like on the Front Range. That's Denver there, versus Iconos. And you can see it's just, there's nothing like it. So in general, you're going to try to avoid using something like these high spatial resolution systems unless money is no object. And one approach you can use is you can subset a Landsat image with a bunch of Iconos images. Use the Iconos, say, to do photo interpretation, and then the Landsat to use classification approaches to map the entire Landsat scene. I don't know why you do that though, because you can get NAIP data that'll let you do the same thing. Some non-photo interpreted uses of this data: water quality and water clarity in urban applications. So looking for areas where you might have non-point pollution sources that are making your water either turbid or promote algal growth. You can map that very easily. Mapping impervious surface, so the amount of concrete and asphalt surfaces, those lead to increased rates of runoff, and so that's something that water and sewer agencies for municipalities want to know about. So this is an easy way to get a map of that. Mosquito control, some places have looked at using high spatial resolution data to look for puddles, essentially, and then direct people out to those points to kill off mosquitoes. We always have a problem with West Nile virus around here, so the Front Range is one of the areas where this has been tried. Precision agriculture, so here on the left, we're looking at an NDVI from an Iconos satellite and you're looking areas that are greener, have greater NDVI and therefore greater vegetation cover. And that information can be used to plan, say, a nitrogen application. So instead of applying the same amount of nitrogen throughout the entire area, you're just going to pinpoint those areas that need the most and therefore cut down on nitrogen pollution and, yeah, cut down on nitrogen use and cost, and also on nitrogen pollution and runoff. Marine applications, these have been very important, particularly with coral bleaching. And I want to talk about something called pan sharpening. So I've said, this high spatial resolution data generally comes with a panchromatic band that's high resolution, multispectral bands that are lower resolution because of these limitations due to the optics and the actual sensor pixel sizes. As well as to some extent the amount of data that you can collect, store, and transmit from the satellite. So you have this bundling of a 4-to-1 ratio of multispectral and high spectral resolution data. And after you've collected the data, there's a process called pan sharpening that can be used to try to reproduce a product that appears multispectral, but with the higher spatial resolution. So here's an example. The simplest way to, well, we've discussed principal components analysis, right? Where we're going to do this analysis on an image. We're going to come up with a series of bands. The first band is going to be brightness, right? So we can take a multispectral image, do a principal components analysis, and create a brightness band and then a greenness band and then whatever other bands are left over. We can then remove the 4-meter brightness band and put in the panchromatic band. Okay, you double up the resolution or the number of pixels of the other bands, but you essentially just insert that band, and then you back transform the PCA, and that leaves you with the original colors, but gives you the appearance of a 1-meter spatial resolution image. So on the bottom you can see a 4-meter RGB image of various different kinds of industrial situations, and I guess some homes as well. And then right above it, the 1-meter panchromatic image, where you've used that higher spatial resolution image to sharpen it up. You're not really getting what it appears to be. As far as your eyes are concerned, it appears to be a higher spatial resolution data product. When you're actually then using these images for further processing, then you're going to run into limitations because you're just going to have edges where the brightness changes, but the spectral data doesn't really change. So that's a limitation. Finally, I want to talk about one more high spatial resolution sensor. This is a concept that's only about 3 years old, and it's putting small satellites in orbit that by themselves don't have very high capabilities, but you put a lot of them in. And the big one in this sector is the Planet Labs constellation of sensors, and you can see each one of them is about 10 centimeters by 10 centimeters by 30 centimeters, I think. So these are very, very small. Each one has a very basic camera on it. It is a frame capture camera. And then you can see they're wrapped in solar panels, and then they beam down to ground stations. And so the individual cameras are not very sophisticated, but you can have these going over multiple times a day. So there's currently, they've launched 360 of these things. There are currently 100 of them still operating. The ground sample distance, the spatial resolution is, between 75 centimeters and a meter. It's a regular frame camera with panchromatic and multispectral. They don't do any kind of radiometric corrections because they're not trying to create a high precision product. What they're trying to do is look at things like shipping lanes, parking lots, what do you call those things? Parking lots, precision agriculture, where you more need a relative measure of what you're looking at than any absolute precise measurement. And so they have a very sophisticated interface to this data so that you can go in and see, individual images from sometimes, depending on what the constellation looks like at any one point, sometimes you're going to be able to get, multiple images a day. More often it's, 3 days between images, provided, unlike this image, that you don't have clouds.